Hi guys, welcome back to Quantum Quandary. Today we're going to do a general Gaussian integral. As you can see here, the integral of x to the 2n e to the minus x squared dx from minus infinity to infinity. Last time we solved it for n equals 0. Of course, we're only considering integer values, positive integers of n. And we're going to consider the integral j of a, which is going to be an extended definition of I0. It's going to be e to the minus ax squared dx. Now, we can find a closed form for j of a by using the substitution square root of ax equals u, whereby dx is du over square root of a. Now, j of a is just going to be the integral from minus infinity to infinity, e to the minus u squared du over square root of a. And since the square root of a can go out in front, we notice that this thing inside is just our I0 integral, so the whole thing is just square root of pi over a. Okay, so j of a is nothing but square root of pi over a. And we can differentiate j of a then. So the first derivative of j of a is square root of pi over a, and then we get another factor of 1 over a with a minus 1/2 in front. Like that. Maybe I can write it in a nicer way. Let's write it as square root of pi here. And then that's minus 1/2 times a to the minus 3/2. That one makes more sense. But that's also equal to, if we differentiate under the integral sign, we get minus x squared e to the minus a x squared dx. Notice that's our I1. So that's, well, actually a minus I1. Let's put minus in front. Just compress this a little bit. So that's minus I1. Okay. Looks like we're getting somewhere. We've got a formula for I1. Of course, yeah, that would be when a is equal to 0. Yeah, let's write that here. A equals to 1, sorry. When a equals to 1, that's minus I1. Okay, so I'm not going to keep writing those, but I'm going to check what the second derivative is. So that's the square root of pi. Now we've got minus 1/2 times minus 3/2, and then a to the minus 5/2. That's, here we have minus 1 squared, right, which is plus 1, x to the 4th power e to the minus ax squared dx, and that would be plus I2 if a were 1. Okay, so now we can see the pattern. The nth derivative of j of a is going to be the square root of pi. Now we're going to have how many? We're going to have minus 1 to the nth power, okay? Then we're going to have 2 to the nth power, okay? And then over here, let's just write it like this first. 1 times 3 times 5, So for the first derivative, we had 1. For the second, we had 3. So it's increasing as like an odd number, right? So that's 2n minus 1. The reason why it's minus 1 is because when n is 0, when n is 1, we have 1/2, right? And then when n is 2, we have 3/2, and so on. So that's why. You can check this out for yourself. And then it's a to the minus. Now here, for the first derivative, we have 3. So that's 2n plus 1 over 2. Okay, and now we can simplify this. This thing, the kind of odd number of factorial, it's represented by a double factorial sign. I'm going to put one of the a's down here. So this is this one. Minus 1 to the n. And then here, I'll put 2 times a to the n. That's all the rest of the a's. And then here, I just have 2n minus 1 double factorial, or whatever you want to call this. Okay, so that's our Jn of A. Now, clearly we're curious about Jn of 1, right? Jn of 1 is just the square root of pi minus 1 to the nth power, 2 to the nth power, 2n minus 1, double factorial. Okay, why are we curious about this one? Because that's what gives us our in's. That's equal to minus 1 to the n, in, minus 1 to the n, because as you can see, this minus, and then this one would have no minus, right? So a equals 2, we get I2, it's plus. So this sign matches this, and so on. So what we end up getting is that this integral that we had, minus infinity to infinity, which is in, minus infinity to infinity, x to the 2n, e to the minus x squared dx, is equal to the square root of pi, which is just I0, times minus 1, times 2n minus 1, double factorial, over 2n. That's it for n from the positive integers. That's it. Hope you guys liked it. Bye-bye.